So the next one we have is around dynamic dimension analysis in ONNX-MLIR compiler. This is another pre-recorded session. This is going to be Chung Lee from IBM, who's going to take us further. Thank you.
We call it analysis in ONNX-MLIR compiler. ONNX-MLIR is an open source compiler to compile an ONNX model to native code using MLIR infrastructure. Dynamic dimension is an unknown value at compile time. It means that we don't know whether two dynamic dimensions are the same or not. Knowing the relationship between dynamic dimensions is key to high performance. We will be able to rule out broadcasting, enable fusion, sim deep code pattern, and determine if an operation is suitable for hardware accelerator or not. ONNX provides an useful shape inference, however, it's not enough for compiler. To avoid boilerplate code, shape inference not only computes shapes during compilation, but also generates runtime codes for dynamic shapes. The compiler often changes ONNX operator patterns so that we sometimes lose initial shape information. Additionally, we have multiple dialects or classes of operators rather than ONNX. To analyze relations among dynamic dimensions, we propose a dynamic dimension analysis in ONNX-MLIR compiler. It currently focuses on discovering dimension equivalence. We can extend this to other types of queries in the future as we see needs. It handles shapes with arbitrary mixtures of static and dynamic dimensions. There are two phases in the analysis. Firstly, we canonicalize shape-related operator by representing a shape by scalar constants and dimensions, then propagating scalars through operators that manipulate shapes, such as shave, slice, or squeeze. After that, we explore relations using existing shape inference infrastructure in ONNX-MLIR compiler. We also provide APIs to query the dimension or shape information when needed. For the first phase, canonicalization, shape operator is often the starting point of calculation. It returns a tensor of integers, storing the shape of the input. However, the tensor means its value is unknown at compile time, so the consuming operator has no dimension information of the shape. As a result, dimension value 128 cannot be propagated to the output dimension of the consuming operator, so it becomes unknown. For complete shape inference, we must start keeping track of shape values that were shaped in tensor. The first step of canonicalizations is to expose individual dimensions to the compiler. In particular, we replace shape operator by a list of dimensions, then concatenate them via concat operator. A compile time value is represented by a constant, while a runtime value is represented by a dimension operator that is an additional operator in ONNX-MLIR. Once individual dimensions are exposed, they will be propagated easily. Let's take an example where we have two operators, slice and unsqueeze, to manipulate shape. Taking a slice of the last two dimensions produces a new concat operator with only the last two dimensions. Then, unsqueezing as the first axis is simply putting a constant 1 in the inputs of concat. Now, we are ready to do analysis. Initially, we associate each dynamic dimension with a unique identifier and put each dimension into a separate set. For each operator, we analyze dimension equivalence in order to expand sets. In this example, we added dimension 3 into sets of dimension 1 and 2. Then we apply transitive closure to merge multiple sets into a single set. We repeat expand and merge sets until a fixed point. Then we finish the analysis. How to expand a dimension set? Given an operator and a dynamic dimension, we would like to find all equivalent dynamic dimensions in the input tensors. For one operator, we can find relationship between output and input, and between input and input. Those are done via shape inference in the ONNX-MLIR compiler. Another way to expand a dimension set is for operator that has an input defining the output shape. In such a case, the input shape was canonicalized into a form of concatenation of scalar dimensions, so we can easily pick up dimensions from the input shape. So we have found several ONNX operators that fall into this category, such as reshape, constant of shape, expand, max unpull, center crop path, and tile. Applying our analysis to the burst squash model, the model has 54 dynamic dimensions, and our analysis groups them into 26 sets, in which one set contains most of the dimension, and each of the remaining sets has 1 or 2 dimensions. The figure on the right-hand side shows how the analysis have closed the gap between combining a static and dynamic dimension. If using static inputs is a baseline, using dynamic inputs costs 28% performance loss, and by our analysis, we can recover 77% of the loss. In the future, we would like to improve the analysis when we have calculations such as addition, subtraction, multiplication, and division. Thank you for your listening.
Thank you. Any questions for the presenters? No questions? Any questions on the bridge? Okay, then to the next one.